The central limit theorem shows a relationship between a population distribution and a sampling distribution. It says that the mean of the sampling distribution is equal to the population mean, and the standard deviation of the sampling distribution is equal to the standard deviation of the population standard deviation divided by the square root of the sample size. These two equations give us a way of making inferences about the population from a sample. Remember, the mean of one sample is the sum of all the values in the sample divided by the sample size. One sample is only one member of the sampling distribution. The mean of one sample almost never equals the mean of the sampling distribution. It's usually impractical or expensive to take a census to find the population mean, and even more impractical to find the sampling distribution mean by taking every possible combination of samples. We need to find a way to use the mean of one sample to learn what we can about the population mean. Let's start using a hypothetical population with an unknown mean and a known standard deviation of 20. From this population, we take a hypothetical random sample of size 4 and calculate a hypothetical sample mean of 80 from the 4 samples. We use the value of 80 as a point estimate of the sampling distribution mean, knowing full well that this is only an estimate. Using this equation, we can calculate the standard deviation of the sampling distribution. That would be the population standard deviation of 20 divided by the square root of 4, which is 2, and makes the standard deviation of the sampling distribution equal to 10. So our sampling distribution has this graph, with a mean of 80. We can be almost certain that the population mean is not equal to 80, but has a probability of being somewhere near 80. And if it has a probability of being near the sample mean, the probability can be represented by an area under the sampling distribution. If we can associate an area under the sampling distribution with a range of possible values for the population mean, we can find a probability of the population mean falling between those limits. For our example, we will choose to find an interval for which we are 95% confident will contain the population mean. The level of significance is equal to the probability of the population mean not being within the limits we calculate, and is always equal to 1 minus the confidence we chose for our interval. We use the lowercase Greek letter alpha to represent the level of significance. The shaded portion under the sampling distribution is 95% or 0.95 of the total area under the curve. The remaining 0.5 is divided equally between the left tail and the right tail. If we could determine the distance each of these limits are from the mean of our sample, we would be 95% confident that those limits would contain the mean of the population. The difference between the mean of our sample and the actual population mean will be the error of our estimate. The amount of error is a function of the amount of confidence we want in the interval. We will see the relationship between the amount of confidence and the error more clearly in a few moments. But first, let's rearrange this inequality a bit. Let's subtract x bar from each quantity to get this result. Next, multiply through by -1 to get this result. And then rearrange so the smaller quantity is on the left to get this result. We'll rewrite the inequality here and make an observation. In this form, the equation shows us that the population mean lies somewhere between the sample mean minus the error and the sample mean plus the error. So x bar minus e is the lower limit of the confidence interval, and x bar plus e is the upper limit of the confidence interval. Now let's develop an expression for e. We can also overlay this problem on the standard normal distribution and put the limits in terms of the z-score. Minus z of alpha over 2 is the left limit of the confidence interval, and z of alpha over 2 is the right limit of the confidence interval. The subscript alpha over 2 is to indicate that it is the z-score associated with half the area of alpha. For our example, alpha equals 0.05. So minus z of alpha over 2 is that z-score that has half the value of alpha to its left. That is, it is the z-score that has an area of 0.025 to its left. And z of alpha over 2 has an area of 0.025 to its right. Recall the definition of the relative standing as the difference between the random variable and the mean, divided by the standard deviation. For the sampling distribution, the random variable is the mean of our sample. Mu is the unknown mean of the population, and the standard deviation of the sampling distribution is the population standard deviation divided by the square root of the sample size. Replacing z in our original inequality, we get this inequality. Keep in mind, our goal is to find an expression for e. Let's now multiply this expression by sigma divided by the square root of n to get this result. Next, we subtract x bar from each term to get this result. We now multiply through by -1 to get this result. By rearranging terms to get the smaller term on the left, we get this result, which is now in the same form as this inequality. That is, we can match their equivalent terms. And the terms of interest are the terms for e and minus e. Therefore, e can be expressed as plus or minus z of alpha over 2 times the standard deviation of the population divided by the square root of the sample size. Let's review. X bar is the point estimate of the population mean. Minus e is the error in the minus direction, making the lower limit of the confidence interval x bar minus e. E is the error in the positive direction, making the upper limit x bar plus e. With this equation, we can calculate the upper and lower limits of the confidence interval. We have the value we need for sigma and the sample size. We still need to determine the value of z of alpha over 2 in order to calculate e, the error. In the next video, we will do just that. We will determine the value of z of alpha over 2 and use this example to show how to calculate the confidence interval.